morning, good afternoon, good evening. Welcome everyone to Luohan Webinar today. So we are very pleased to have Professor Xiang Hui. So Professor Hui is a professor in the marketing area at the Olin Business School at Washington University in St. Louis, as well as a digital fellow at the Stanford University Digital Economy Lab. Professor Hui studies the design of information mechanism and economics of digitalization, drawing theory-driven insights from large-scale data sets from industry collaborations. His latest research includes designing trust system on e-commerce platforms and quantifying the economic impact of nascent technology. Today, Professor Hui will give us a talk about his new paper, When and Why Buyers Rate in Online Markets. Professor Hui, you have 90 minutes and the floor is yours.
Thank you very much, Xiang Hui, for the introduction. And I also want to thank you and the rest of the seminar organizers for the invitation. So today I will talk about my newest work, like Xiang Hui has said, which is about when and why do buyers rate in online markets. So this is joint work with Toby Klein at Tilburg and CIPR and Konrad Stahl at the University of Mannheim, CIPR, CESIFO, and ZEW. So to briefly motivate, online ratings are an important source of information. And the key feature of these ratings is that they are voluntary. And because of that, previous work has shown that ratings are left selectively. So for example, on eBay, which is going to be our empirical setting, buyers leave ratings for about 2/3 of the transactions. Okay. And besides selectivity, previous literature has also shown that the rating distribution tends to be very asymmetric. In particular, aggregate ratings are often very favorable. And in marketplaces where we have finer scale rating distribution or rating scales, like a 5-point scale rating, then we have typically seen the so-called J-shaped distribution, where a majority of the ratings are at 5 stars, then we have a few 1 stars, and essentially very few in the middle. Now, because ratings are left selectively, the argument has been made in the previous literature that these ratings are essentially not quite informative. Now, the goal of our paper is to essentially better understand this statement, right? Which is to understand what can we learn from these ratings, despite the fact that they are left selectively. And our key argument is that, in order to answer this question, we need to first understand the process that buyers use when they leave feedback, or in other words, when and why do they leave feedback. Now, the approach that we take to address this question is that first, we're going to propose a reduced form Bayesian model of buyers rating behavior. And that model is going to generate a few testable predictions, which we take to data from eBay. And lastly, we are going to calibrate the model to to moments in the data and perform some simulations. And the key takeaway of our paper is that buyers may learn about the quality of a seller in about 100 transactions or in about 65 to 70 ratings, even if online ratings are biased. By the way, at any time of my talk, feel free to interrupt me with your questions. Okay. So without further ado, let me jump right into the model. So the idea of the model is very simple, which is that buyer's utility from rating is going to increase in the amount of learning from her transaction. So note that this is a reduced form model in the sense that we don't give a specific reason why utility of rating increases in the amount of learning. So for example, this could be some altruistic reasons that a buyer thinks that when she learns the most, or when she learns a lot from her transaction experience, others would also benefit a lot from her sharing the experience, and therefore she's more likely to rate due to some altruistic concerns. Could be that. Could also be due to some selfish reasons that a buyer wants to tell other buyers or the platform that this seller is of high quality, and therefore this buyer will be more likely to encounter these high quality sellers in the future. Okay, so there could be all of these reasons, but the model is simply stating that the utility of rating increases in how much I learn from my experience. Yes.
Yeah, just curious whether this idea is an assumption or is a result that hypothesis that you want to test on.
It's an assumption, and that's going to generate a few predictions on essentially how my belief about the seller's quality is going to affect my rating behavior. And those predictions are the ones that we're going to test using data from eBay.
Okay.
I'm sorry, can I have one? I have one more question.
Sure.
How often did you find that the seller's feedback was initiated by buyer's feedback was initiated by the seller, like a person that was selling told their friends to go out and push that this was a great product?
Sorry, you mean, can you repeat your question? I didn't quite get that.
Yeah, so
you're kind of
so
dark.
I'm sorry, I'm outside. Yeah,
no worries.
Because my kids are asleep.
Thanks for coming.
My question, thank you. My question is we've seen in certain other platforms, maybe not eBay, but Amazon, that they've searched for people that have relationships with the seller, have searched their friends to give positive feedback. So how does that?
I see. So you're saying that there's some sort of social network components to it. So
yeah,
on eBay,
go ahead.
So on eBay, that's not the case, because you can't sort of be friends or unfriend with someone. But that's sort of an interesting.
But I mean, like for even for Amazon, I know people on an Amazon platform that have said, I'm selling these products in like a handbag, and they said, can you go buy one and leave positive feedback? Is that not happening on eBay?
I see. That's so you're talking about fake review.
Right. That's my question. Thank you.
Yes. So that's a tricky question, because I'm not supposed to say anything about fake review on eBay due to my data agreement. What I can say is that the cost of leaving fake feedback on eBay is relatively high, in the sense that you kind of have to buy the product yourself, therefore pay platform some fees in order to leave a wrong negative feed or a fake feedback, right? So that's not to say that this does not happen at scale, but based on what eBay claims, and that doesn't seem to be happening at large. And the second thing that I want to say is that the focus of our paper is essentially to understand what's the effect of belief, right? What's the effect of belief and belief updating that the seller is of a high type on my rating behavior. Okay, so in some sense, we're taking this fake review as given, and we're saying that, hey, in the presence of whatever fake review is out there, what's the effect of belief updating on my subsequent rating behavior? So that's going to be the focus of the current paper. So I hope that
got it. Thank you. Your question. Yeah, that totally helps. Thank you.
Yeah, no problem. So going back to our model, so we have probably the simplest Bayesian model. So first is a binary model, in that seller is of either high or low quality. And we also have binary signal, in that when the seller is of high quality, then the transaction experience is good with probability rho high. And when we have low quality seller, then the transaction experience from that seller is going to be good with probability rho L. Okay, so that probability is smaller than rho H. Now, buyers has a prior belief that a seller is of high quality based on some public rating profile. The buyer buys, and when the transaction experience was good, then her posterior belief that the seller is of high quality is given by this formula. Okay, so mu G is the posterior belief after having a good experience, and that's going to depend on her prior belief and the two rows, okay, in a Bayesian fashion. So there are a couple of notes that I want to make about this bullet point. So first of all, in this paper, we don't study buyer's purchase decision. Okay, so our focus here is essentially that conditional on transactions has been made. How do buyers decide when to rate and how to rate these sellers? Okay, so we're actually currently working on a paper that also endogenize the endogenous matching process between buyers and sellers in the first stage, but that's not the focus of this paper. And empirically, we are essentially going to leverage our first research design and second covariate adjustments to argue that essentially conditional on the design and the covariates, matching is random. Okay, so that's how we think about this problem in this current paper. And the second note that I want to make is that in the presentation, I'm not being very explicit about what is the relationship between buyer's prior belief and this public rating record. So we have a discussion and proof of that in the paper, but it turns out that this relationship is not very important as long as a buyer's prior belief increases in the seller's public rating record. Okay, and for an example of a public rating record, you can think about, if you're familiar with eBay, you can think about a couple of metrics that eBay reports on seller rating, which is first the share of ratings that are negative, right? So percentage positive ratings. And the second metric is feedback score, which is essentially number of positive feedback minus number of negative feedback. Okay, so those are the two things that buyers are going to see in the case of eBay. Now, we assume that the buyer, the typical buyer, right, in our model is going to share her experience by leaving a review or rating if the utility of leaving a feedback is higher than some idiosyncratic cost. Okay? So a key term in this utility on the left-hand side is this Bayesian difference, okay, which captures the amount of learning in absolute terms. So this is the essentially posterior belief after incorporating my own good experience minus my prior belief. So essentially, the more I learn from my own experience, the more likely I'm going to share by this factor of B1, and B naught G is the baseline inclination to rate when I have a good experience. And similarly, the posterior belief after having a bad experience is given by mu B, and the buyer rates if the utility of sharing that bad experience is higher than C. So again, we have this Bayesian difference term, right? Mu posterior belief after having bad experience minus mu, and we allow the baseline inclination to leave a negative feedback to be in general different than the baseline inclination to leave or baseline utility to leave good feedback. Okay, so this might reflect the fact that people might be in general more reluctant to bad mouthing sellers. Okay, so this is the very simple binary Bayesian model that we have. So do I have questions in the chat or? Presumably that sort of priming, not sure what the official term is only for new products.
Are
Yes.
you going to quantify the bias or how the bias come into?
Yeah, I'm going to define what I mean by bias. Yes, it's going to become clear in a moment.
Okay.
And did you ask the question on the chat or it was someone else?
I guess it's somewhere else.
Okay, ignore that. All right. Okay, so this very simple reduced form model is going to generate a couple of predictions. So suppose that our prior belief is sufficiently high, okay, and this is sort of the interesting range where transaction took place, right? Because if prior was low, then probably transaction wouldn't have taken place to begin with. Now, suppose this is the case, then that simple model predicts that the likelihood that a rating is left decreases in my prior belief that the seller is of high type, right? And this essentially comes from this binary Bayesian model where, if a seller has a higher prior, then I'm going to put more weights on that prior and less weight on my own transaction signal when forming that my posterior belief, right? And that prior of the seller is stronger. If that prior belief is stronger, then that means that my posterior belief after incorporating my own signal is not going to be that different from my prior belief, right? And therefore, I'm less likely to have a deviating posterior relative to prior. And based on our simple model, that's going to lead to a smaller Bayesian difference, and therefore I'm less likely to rate as the seller's prior increase. Now, the second prediction says that, suppose now we have a negative shock to our prior belief, then that's going to lead to two things. So first, it's going to lead to an increase in the likelihood that a rating is left, right? And this is essentially the reverse of the first prediction, right? That if you have a negative shock to your belief, then I'm going to assign less weight to the prior and more weight to my own signal. Therefore, I'm more likely to have a deviating posterior and hence a larger Bayesian difference, right? And therefore, I'm more likely to rate. The second prediction says that this negative to shock to belief is also going to increase the likelihood that a given feedback is negative. Okay? So what this means is that essentially the first results, this increasing in likelihood that the rating is left, is going to be disproportionately larger when you have a negative experience compared to when you have a positive experience. And this comes from the mechanics of this Bayesian model that essentially if your prior is very high, then you learn more from a negative experience than the amount that you would learn when you have a positive experience. Okay? So that's the second part of the second prediction. Now, in the next two slides, I'm going to show you some visualizations so you can see the two predictions by eyes. Right? So in doing these examples, I'm going to assume a couple of parameters for the rows. Right? So row G is 95%. So this means that if you're a good seller, then you provide good experience 95% of the time. Whereas if you're a bad seller, then you provide good experience 80% of the time. Okay? So we think that these numbers are more relevant for e-commerce platform these days because even if you're a good seller, in order for you to be relevant or appear in the search results, you kind of have to have some level of quality. Okay? Otherwise, you will be essentially weeded out by various other trust mechanisms that platforms have, like quality certificates, search ranking, and warranties, and so forth. Okay? So we think that these are relevant for e-commerce these days. And in order to plot the probability of rating, we also need to assume values of the utility function, right? And these are essentially calibrated values from our last exercises. Okay, so in this graph, we plot the amount of learning, right, or the changes in belief, right, posterior minus prior, as a function of my prior belief that the seller is of a high type. And we plot this curve for a good experience on the top and a bad experience at the bottom. So in order to see the first prediction, right? So suppose that our prior belief is relatively high, right? Say 70% and above, because this is the relevant range. Then as my prior increase, I'm going to learn less and less from my own experience. And this is true for both a good experience and for a bad experience in terms of absolute value. Okay? And therefore, according to our simple model, I will be less likely to share either good or bad feedback or bad experience when prior increases. Okay? So that's the first prediction. Now to see the second prediction, suppose our prior is high, like close to 1, then a negative shock to prior, right? So that I'm moving to the left, is going to increase my probability of both leaving a positive experience and a negative experience. And in addition, I'm much more likely to leave a negative experience, right? So given the rating, it's much more likely to be a negative experience than a positive experience. And this comes from the fact that, I learn more from a negative experience when my prior for that seller is high. Now in this figure, part of this asymmetry is driven by these asymmetric rows, but we have shown in the paper that even in cases where the rows are the same, meaning that rho G equals to 1 minus rho B, then we would still have this asymmetry. Okay, so it's coming purely from the mechanics of a Bayesian model. Now we can also plot the probability that the feedback is left as a function of my prior. Okay, again, for a good experience and for a bad experience. So we can again visualize the two predictions, right? So suppose our prior is high, like 70%. Then as my prior increases, I'm going to be less likely to leave a positive or a negative feedback. And the second prediction says that if there's a negative shock to my belief, then I'm going to be more likely to leave a negative feedback and also more likely to leave a positive feedback. And a given feedback is more likely to be negative because essentially the second curve has a steeper slope relative to the slope of the first curve, right? So that's how we can see the second prediction from the graph. Now, going to Xuan's question about how we think about rating bias in this case, what our model says is that the probability of leaving a rating is going to depend not only on your transaction experience, but also depends on the amount of learning from your own signal. And that amount of learning is in turn a function of my prior belief that the seller is high. So that means that in general, percentage of positive ratings is not the same as percentage of good experience, right? Because percentage positive rating also captures the amount of learning. And the difference between percentage positive ratings and percentage of good experience is going to be defined as the rating bias in our case. Okay. All right. So if there's no questions, then I will move on to the empirical tests. Okay.
Excuse me.
Yes.
I have two questions. First, about the asymmetry. How is that possible if the signal matrix is symmetric, but you have, I think, is that relies on the assumption on mu, because mu is
so essentially what we proved in the paper is that if the signals are symmetric, what you're going to have is that you're going to have a larger hump shape for the top curve, right? And what you can show theoretically is that the peak of the hump for the good experience happens before the peak or the trough for bad experience. And because of that, you're always going to learn more from a negative experience when your prior is high. So this asymmetry actually is not dependent on these asymmetric rows. So that's how it works.
And also, correct me if I'm wrong. So I think this is a mix of a good news learning and bad news learning, right? So basically, you learn whatever, whenever the quality is good or bad, you have a chance to learn the respective signal. And
right. So I'm not sure if I understand you correctly, but so here, basically, a signal is not fully revealing, right? So even if conditional on my signal, I'm not exactly sure what type you are. And these graphs are saying that, hey, conditional that I have a bad experience, what's my amount of learning? And the top curve is saying that, conditional that I have a good experience, how much do I learn as a function of my prior. So I hope that
I ask this because I think in the learning literature, good news learning and bad news learning have very different mechanisms. I worry about like the asymmetry come from there, but I think it's fine now. And I have another question. Can you justify more about why the motivation of leaving a rating is positive related with this change rather than the absolute probability of think it's a bad or good?
So are you saying that so basically in our model we're saying that I'm more likely to rate if the Bayesian difference is higher. So you're saying that why is it not?
If it's really good, I know it is good, and then I
so you're saying that this term should not be the posterior, but my signal, basically, right? So essentially, you're saying that,
or some mix, or I'm just saying can justify more about why you choose this as a
right. So so essentially so there are a couple of things. So just to understand what you're saying, so you're saying essentially that perhaps this is should not be posterior, should be just my experience. So it's some sort of rating by surprise story that my prior belief of this guy is high, and then I get a experience which is super bad, and therefore I would be more likely to rate without incorporating that signel into my prior belief to form. Okay.
So like I know this book is good, and then I read it, so I want to share.
Bad, and therefore I want to share.
Good or bad, and or extremely for me, like I only share when it's extremely good. I want to share to others. Or it's extremely bad, but not depends on my prior.
Right. So a couple of things. So first, theoretically, the way that we think about this is that this Bayesian difference essentially captures my confidence of my own signal relative to my prior belief. And the reason is that essentially, in a binary Bayesian model, this rho also captures the signal noise, right? Variance of my signal, because it's given as rho times 1 minus rho. So essentially, the higher the prior belief that I have, the less noisy that signal is, and that's by construction. And therefore, I'm going to use that signal or prior belief, like give that more weights when I form my posterior belief. And the idea here is that, when I have a deviating posterior, then that means that I'm more confident about my own signal, right? Or I'm less confident about the prior belief that I had, and therefore I'm more likely to rate. So there's some sort of a confidence thing going on. And then when I report this experience, I'm going to report my signal, okay, rather than how much I learn. And the reason is essentially that on eBay, you can only sort of rate positively or negatively, but you can't say, hey, I'm 60% confident that this is a good experience, and so forth, right? So this the way of setting this up is also sort of motivated by the setting at eBay, right? Or you can think about some other settings like going to a trial, right? So whether I want to, stand on a trial and provide evidence depends on how confident I am about my own evidence relative to existing evidence. But when I'm sort of standing on that trial, I'm sort of obligated to tell the truth or to report my experience rather than sort of reporting this Bayesian difference. So that's, I guess, my answer from a theoretical point of view. Then from an empirical point of view, our model is, or our data is also consistent with this essentially rating based on this Bayesian difference rather than rating based on surprise. So essentially what's going to be different is this graph, because here, if you're rating based on this Bayesian difference, then if your prior is high, then you're less likely to rate, right? Whereas your model, or the model that you suggested, would predict the opposite, that if you have a high prior and I get a negative signal, then I should be more likely to rate. So that's essentially not kind of what we see in the empirical test. So that's the second part of the answer.
I see. Thank you.
Yeah, no problem. And I have a question from Jin.
Yeah, hi. So I'm just wondering that, have you noticed any price changing with the rating dynamics in your data? like
Right,
whether
right.
seller can manipulate the prices, right, after
Right.
seeing some dynamics in ratings. Yeah.
Right. So that's a very good point, and I'm going to show you a graph when I'm going to essentially plot a graph on the price that seller charges as he becomes more established on the platform. So I will get to that point.
Okay, thank you.
Yeah, and let me know if that sort of doesn't answer your question. Okay. All right. So this screenshot, was taken back in 2021, and it essentially shows that eBay has a lot of visits per month. So it's definitely a relevant e-commerce platform globally. Now here's how we construct our data set. Okay? So we start with sample 0, which is essentially to look at, to first find all the sellers that entered eBay in March 2011, where entry means that they started their first listing ever on the platform in that particular month. Okay, and the reason we choose 2011 is because there's no major reputation-related policy change in that year. And then all of these sellers that entered in March.
Oh, sorry, excuse me.
Yeah.
I'm sorry to interrupt, but can we pause for 1 minute, because we in China there is a memorize for the May 12th earthquake today.
Oh, okay, yeah. Okay, please, yeah.
Yeah, okay, thank you. Yeah, we just 1 minute. I think. Okay, everyone, I think we can go ahead. Thank you all. Thank you.
Yeah, problem. Good. So essentially, this we look at all the sellers that enter in that month, and we look at their transactions in the first year after they enter. Okay, so that's our starting point. And then from there, we construct a balance sample, okay, called sample 86, which is going to be the focus of today's talk. So here we essentially first find sellers who sell at least 86 transactions in the first year after they enter. And this corresponds to the top 5% of the sellers out of all sellers that entered in the same cohort. And then all of these sellers, we're going to get their first 86 transactions. Okay, so we have a balanced sample in that for each seller, we have 86 transactions, and second seller, 86 transactions, and so forth. And the reason that we want a balanced sample is so that we can essentially track over time what's the probability that the rating is left as a function of this transaction index, and interpret it causally without sort of dynamic selection problem. Okay, and just to give you a sense of why this sample is relevant. Yes.
It's CJ here. Can I ask one question related to this kind of sample? Because once you have all the sellers with at least 86 transactions, then you're gonna have kind of then you still have the kind of the timing of each transaction.
Yes. So I still observe when each transaction.
Yeah, because I was thinking that your probability to rate, it also depends on your outside options and also the kind of other product available at that moment. So is there a problem for this kind of thing? If you only...
So I mean, these are only sellers that entered in a particular month, right? So their biggest competition is like with other sellers, right? All the established sellers.
Yeah, if the 86 transactions spend a long time, then they're gonna compete with new cohort, right? So in that case, maybe
that's interesting. That's interesting. So I agree. So in our current analysis, we kind of don't control for calendar time, right? So we basically have, in our specification, we're going to have this transaction index, fixed effects, but you have a very valid point that, maybe this transaction, for some sellers, these transactions all happen within a few months, whereas for the others, it's spread it out across a year. And demand, underlying market condition, competition can be all different across these years. And I think that's a good point. What we can do is to maybe further restrict on same calendar time, for example, or sellers with this similar sales velocity, and then redo our analysis. Yeah. Thanks. So just to sort of give you a sense of whether sample 86, why sample 86 is relevant. So even though this is top 5% of seller, right? This is only 5% of seller, but the amount of the transactions that they made among all sellers that entered in the same cohort is about 40 to 50%. Okay, so these sellers account for half of the transactions in this cohort. And also, if you look at the sellers in sample 0 who do not make it to sample 86, right? So there are two parts. So first, 75% of the sellers in sample 0 who do not make it to the sample 86 essentially exit, okay? Where exit means that they do not have any sales in the second year after they enter. Okay, so most people die or don't survive in the first year, in sample 0 that don't make it. And then the other 25% of people, they make it to the second year, but they just simply do not sell more than 86 items. So if you look at these sellers, their average quality score or average consumer reports is actually very similar to sellers in sample 86. Okay, so essentially what we are finding from these sellers from sample 86 can also speak to sellers in sample 0 who do not exit. So that's sort of the awards on representativeness of the sample. And lastly, for robustness reasons, we also look at sample 338. Okay, so these are sellers with at least 338 transactions in the first year, and we take their first 338 transactions. Okay, so it's for robustness reason, which is not going to be the focus today. Okay, so let me show you some summary statistics of our sample. So first, in panel A, we report some seller level characteristics. So one observation is the seller here, and different columns corresponds to sample 0, sample 86, and sample 338. So essentially, the first 2 or even 3 variables are about seller size, right? So it's seller sales volume in the first year, the number of transactions in the first year, and number of unique categories that they sell in their first year. So, if you look at these 3 metrics across columns, you see that these numbers get bigger as you move to the right, and that sort of makes sense because sellers that survive and get into these samples are essentially larger sellers. Now, if you look at a feedback rating, which is eBay percentage positive, which is given as number of positive divided by the sum of positive and negative feedback, then we see that this number also increases across columns, right, as you move to the right. And so essentially it's reflecting that, sellers in a later sample are on average higher quality, right? If you think that higher size is correlated with higher quality, then this is perhaps not surprising. And another reason is essentially this selection effect that, sellers who do not make it from sample 0 to sample 86, are those that essentially receive a very negative rating early on, and therefore they have to sort of exit. Okay, so that's essentially explains these differences. Now in panel B, we look at the characteristics of buyers who purchase from sellers in different samples, right? So here one observation is a buyer. The first couple of variables are about buyer experience, both in terms of their number of previous transactions on eBay and, essentially whether they registered, 2 years before the sample. And we see that, if you move to the right, sellers are essentially getting more experience. So this is saying that essentially more experienced sellers tend to transact or buy from higher quality sellers on average, right? And then lastly, if we look at buyers' inclination to leave feedback, in the year before, and also what is the percentage of negative feedback that they left in the year before, then these numbers are sort of by and large similar across the three panels. I guess especially for buyer criticalness, right? The share of ratings that are negative is not sort of too different across these samples.
Hi, Xiang.
Yeah.
I have one question regarding this buyer characteristics. It's quite interesting to find that the more experienced buyers tend to buy those larger, those kind of more sample with longer durations. I was wondering whether it's due to the sorting on other dimensions of products, or like quality, or like price and other types of variables, or due to the buyer's kind of ability to find the right seller.
So a big thing, and this is, I think, relates to Jin's point, is price, right? So I agree with you. Like ex ante, I would sort of expect that experienced buyers would buy from sort of new sellers, because essentially they can observe some other signals that tells them whether the seller is of high quality or not, despite the fact that they lack past history. And also these sellers are more likely to charge a lower price, right? So you would think that matching would go the other way, but it seems like that was sort of not the case, at least not the case in our sample. And as I will show you in a graph a little bit, we actually don't see that, essentially sellers are charging higher and higher price as they get more established in our sample 86. And I'll sort of get to that graph. All right. Now in panel C, we plot or we report transaction characteristics. So first, we report the share of transaction or share of repeated transactions. So we see that these shares are relatively small, right? It's roughly 1 in 6. So that means that reputation mechanism or information mechanisms in general has a large scope or has a large role to play in case of eBay, right? Because it's not like people are repeatedly buying from the same seller. And then if we look at share of transaction in which a feedback is left, it's about 2/3 across the samples. And the next three metrics are essentially share of transactions with negative consumer reports. And we have 3 types of consumer reports, right? So first, feedback is the classic rating system. And then we also have low detailed seller ratings. So detailed seller ratings are essentially, I think Taobao also has this, that essentially buyers can rate sellers in 4 dimensions, like items described, shipping, and so forth. So compared to classical feedback, these detailed seller ratings are less observable by future buyers, because a future buyer actually has to click on seller's profile in order to see these detailed seller ratings. So these are less observable than classical feedback. And lastly, claims are cases where buyers essentially privately file a complaint to eBay, right? Either because item not as described or item not arrived. So these claims are essentially unobservable by future buyers at all. And essentially, we're going to leverage these negative reports that are less observable as placebo test later on for our empirical analysis. But for now, you see that these metrics are quite consistent in that share of negative reports decreases as you move towards right? So that's saying that essentially bigger sellers are better in terms of having less negative consumer reports. And lastly, the number of days, there's a gap of about 13 days between when transaction took place and when feedback was left. So I'm guessing that on Taobao, this gap is probably smaller because logistics in China is probably much faster. But anyhow, so this is the gap that we have, and we are going to also leverage this gap for one of our research designs later on. All right. So now let's go test our theoretical predictions. Okay. So the first prediction says that, as my prior belief that the seller is high quality increases, I'm going to be less likely to leave a rating. Okay? And in order to show that, in this graph, we plot the share of transactions with any feedback left and share of transactions with any detailed seller left, the detailed seller rating left, as a function of a seller's transaction index. Okay, so meaning that 1 means the seller's first transaction, 2 means seller's second transaction, and so forth. Okay. So the idea of using transaction index is that, essentially on eBay, most of the ratings are positive, right? So about 98% of the feedback left are positive, and therefore, increase in transaction index is very correlated with the increase in prior. And as a robustness checks, we have also replicated the results, but using number of positive feedback received to date as the x-axis, and the result is exactly the same. Okay, so so that's not driving the results. So what we see in this figure is essentially this decreasing likelihood to share an experience, which is sort of consistent with this first prediction that, as my prior belief changes, or as my prior belief of a seller of high type increases, then I'm going to be using my transaction signal less and less, and therefore I'm less likely to rate. Now, of course, there could be, alternative hypotheses, which is that, perhaps there's time trends, as Shijie was sort of briefly alluding to, and there could also be changes in products that the seller is selling over time. It could also be that, perhaps seller is getting matched with buyers with different level of criticalness or different baseline inclination to leave a rating. And the way that we're going to sort of deal with this is to first essentially do this covariate adjustment approach, right, where we, successively control for different fixed effects like month fixed effects and product fixed effects in our regression, as well as controlling for buyer experience in our regression. So that's sort of our first attempt to control for these selections on unobservables. And by the way, this regression is essentially is to quantify this negative slope in the previous slides, right? So it's regressing whether feedback is left on this transaction number, okay, divided by 10. So now the problem though is that, it could be that selection on unobservables happen at the match level, right? It could be that, so essentially we kind of want to control for a buy seller fixed effects, right? To account for selection that's happening at this endogenous matching level. But the problem is that because share of repeated transaction is low, if we do that, then we essentially don't have variation to identify anything. And the way that we sort of address this selection at the match level concern is to essentially dig into previous literature and to think about, what are some particular reasons of selection at the match level. Okay? So the dominant story that's been given in the previous literature, right, such as the one in Acemoglu et al. 2018, is essentially these changes in consumer surplus story, right, which is also what we talked about. That essentially, when the seller just entered the platform, there is some cold start problem, so that the seller has to kind of charge a low price to kind of solve the cold start problem, and as a result, sellers who buy from these new sellers are going to have a higher consumer surplus. And as a seller established on the platform, they're going to charge a higher and higher price, and therefore a consumer surplus will be smaller and smaller over time, and that might explain the decrease in probability of leaving a feedback. Okay. Now, in order to test whether that story is dominant in the case of eBay, we come up with a couple of surplus measures. Okay. So the first consumer surplus measure is to essentially look at auctions. So on eBay, the auctions are essentially second price auctions. right? Where the winning seller the bidder with the highest bid is going to pay the second highest bid plus an exogenous small increment. Okay? So it's very similar to a second price auction. And assuming that buyers are playing their dominant strategy, then the difference between the highest bid and the price that they end up paying is a proxy for consumer surplus. Okay? And on the in the graph on the left, we essentially plot, how this consumer surplus measure changes as a function of transaction index. And as you can see visually, this thing actually does not change that much as seller gets more established in our sample. And if we control for this in the regression, it essentially doesn't do much. Okay. Now on the right figure, we use not only auctions but also posted price formats. Okay, and we only look at items that has a product ID defined in new conditions so that we can do apple-to-apple comparison. And here essentially we regress price on this feedback index and a bunch of fixed effects and see whether we have a sort of increasing trend of price over time. And based on the graph on the right, we don't seem to see that. So that suggests that changes in consumer surplus does not seem to be the driver of a decreasing rating probability in the case of eBay, at least in the sample that we're looking at. Okay. All right. Now let's move on to the test of the second prediction. Okay. And just to remind everyone, it says that if the prior is sufficiently high, then a negative shock to belief is going to increase the likelihood that any rating is left. And second, it's going to increase in the likelihood that a given rating is negative. Okay. So the argument is the following, that if a buyer's prior is very high, then again, the buyer will not learn much about seller quality from the signal that she receives in the transaction. But now suppose in another world, right, counterfactually, another buyer actually left a negative feedback. So that means that in that counterfactual world, the focal buyer would have a lower prior belief that the seller is of high type. And now in that world, she would learn more from her own experience, and therefore she'll be more likely to rate. Okay? And we also show that the effect is larger for a negative experience than a positive experience in the analysis I'm going to show you. Now, the challenge here is, of course, that how can we sort of get a clean shock on just the belief, but it's otherwise uncorrelated with quality, right? So for example, if you use just the arrival of a negative feedback as a shock, then yeah, that's going to change future buyers' belief that the seller is of high type, but that probably is also correlated with underlying quality, right? So in other words, if we observe consecutive, say, negative feedback in the data, then that might be due to transitory quality shocks. So a seller, say, sampled just a batch of low quality products, right? And if this batch of low quality products happen to be sold around the same time, then we're going to see a bunch of negative feedbacks arriving, but that's not due to me leaving more negative feedback because my belief updates, but rather it's just coming from the fact that all of these are low quality products, right? So that's the identification challenge. So the approach that we take here is essentially to study the effect of a negative feedback that was given by mistake. Okay, and on the next slides, I will tell you exactly how we know these things and what are the assumptions that we are making. Okay? But for now, suppose that we know that there are negative feedbacks that are given by mistake. Then the idea of identification is that these ratings are not meant to be negative, and therefore they are uncorrelated with the underlying seller quality. But unlike us, who have access to eBay's data, later buyers on the platform do not know that these negative feedbacks are wrong, and therefore they update their prior belief regardless. And we're going to essentially quantify what's the effect of belief updating, which we argue is due to this mistaken negative feedback on my subsequent rating behavior. And I have a question from Jin.
Yes. I'm not like quite sure about how consumers on eBay observe the ratings. So they can observe the complete sequence of ratings, or average rating, or just recent ratings.
Right. So here on eBay, when you try to leave a rating for sellers, you're going to see essentially that seller's feedback score, which is number
like before buying. So
before buying and also before rating. Yeah.
Okay. So you can see the average rating.
Right. So you can also see the average rating. So the thought experiment is that, you know, there are two worlds, right? Two counterfactual state of the world, same buyer, same seller, same everything. The only thing that differs is that, you know, in the first world, say the buyer sees 100% positive feedback, whereas in the second world, the buyer sees, you know, a 98, for example, 98% positive feedback because of this additional negative feedback that we argue is left by mistake. And we're going to quantify essentially what's the effect of this wrong negative feedback on outcome. And we're going to attribute that effect as the effect of belief updating, right? But changes in my belief that the seller is of high type on my rating outcome. So that's the thought experiment.
Okay, yeah, because in a theoretical world, I would imagine, like, if consumers are aware that there is a certain probability of noise, and then say they have seen, like before this noisy rating, like all of a sudden there is a negative one, and that there has been like 100 positive ratings established, and then perhaps the public belief is already updated to nearly one, right? Mm-hmm. The extreme state. And then they will interpret this noisy rating as a noisy one instead of, do Bayesian updating or
definitely. Yes. So that part is accounted for in the model. In that, so definitely, like if you have essentially 99% positive feedback with 10 ratings, well, I guess not with 10, like 90% feedback with 10 ratings, versus 90% feedback with 100 ratings, then my prior belief for that seller is going to be different. So that part is sort of accounted for. Okay. And to your point, I'm going to show you a result, essentially heterogeneous treatment effects, depending on whether the seller has a lot of prior positive versus not. And I'm going to show you that the directional change of that, or the heterogeneous treatment effects, depending on the seller's prior, is consistent with the Bayesian model that I'm presenting.
Okay, thank you.
Yeah, no problem. So once we have these, shocks, right, wrong negative feedbacks, then we can evaluate it with a simple, essentially DID model, where on the left-hand side we have rating indicator for seller I and transaction index T. And on the right-hand side, we have this transaction index fixed effect, right, to capture the fact that rating probability decreases over time. And then we have a treatment dummy for each individual seller I that indicates whether the seller is in the treatment group, meaning that he has received a wrong negative feedback, or in the control group, meaning that the seller did not receive a wrong negative feedback. So this beta is going to capture the baseline difference in rating probability across these two groups of sellers, right? This could be due to the fact that they sell in different markets, and therefore consumers are differentially critical, and so forth. So beta captures the baseline difference, and post IT indicates whether transactions are after the wrong negative feedback was received. Okay, so it has subscript IT. So essentially, this number is going to be 0 for sellers in the control group, and it's going to be 1 for sellers in the treatment group after they receive the wrong negative feedback. Okay, so we're interested in essentially this gamma. Okay. Now, as I promised, I'm going to talk about how we know this mistaken negative feedback. So the reason we know this is because buyers and sellers on eBay have to go through a structured process in order to revise a negative feedback. Okay, so in particular, a seller is going to initiate this revision process. And the seller has to choose among one of the three reasons, right? The first one is that I resolved the problem with the buyer on this transaction. The second reason is that the buyer confirmed that he had accidentally left the wrong feedback, and other. Okay. So the reason that we think that a seller would truthfully choose this reason is that, first of all, there's only one chance for revision. So that means that if the seller sort of chose the wrong reason and the buyer denies it, then the case is closed. Okay, so the seller will be stuck with this negative feedback forever. Okay, so there's a limited attempt, or one attempt per transaction. And in addition, eBay only uses this information for feedback revision reasons, in the sense that it does not affect a seller's search ranking results or getting quality certificates or any other ways. Okay, so because of these, we think that it's unnecessary for a seller to suggest that the buyer is at fault, that she has left the wrong feedback, if that was not true, right? Because even think about the case, think about the case where even if the seller has bought off the buyer, right? So that, hey, I'm going to give you $100 so that you remove this negative feedback. Even in that case, given all these features on eBay, it's sort of not necessary to suggest that the buyer has made a mistake, right? He can simply choose other, or that I've resolved the problem with the buyer, so that you will be sure that the buyer will be happy with the choice and therefore revise the negative feedback. Right. So if anything, the bias would go the other way, that we are undercounting the amount of wrong negative feedback, or we're including some of the treatment cases in the control group, okay, which creates some attenuation bias. But this is sort of how we identify these shocks. And here's our results. Okay, so in the first column, the outcome variable is an indicator of whether a feedback is left. And the treatment dummy, captures the baseline difference, and this number is what we're interested in, right? It's the gamma parameter in front of post. So this first column tells us that after receiving a wrong negative feedback, the likelihood that the feedback is left is increased by 4.7 percentage points. And note that this is a large increase because the baseline inclination to rate is about 65 percentage points, right? So it's 5 over 65. Now, in the second and third column, right? So this, results from this first column is essentially consistent with the first part of the second prediction, right? That if there's a negative shock in prior, I'm more likely to leave any feedback. And then in column 2 and 3, we essentially break this feedback into positive and negative feedback. And what we find is that the percentage increase for a negative feedback is essentially larger, okay? Because the baseline for leaving a negative is only 1 percentage point. And because of this estimates, or according to this estimates, that likelihood has increased from 1 percentage points to 2 percentage points. And that's 100% increase, whereas the increase in likelihood of rating positively only increases from 65 to 68.7 percentage point. Okay, so this is saying that conditional on the feedback left is actually much likely to be a negative feedback than it being a positive feedback. Okay, so that's consistent, essentially with the second part of our prediction too. And by the way, we don't have a lot of power here because even though we have a lot of observations, wrong negative feedback are rare instances, right? So we actually only have about 250 of these cases in our entire sample. So that explains the lack of powers here. But when we replicate the results using sample 0, okay, which contains many more sellers, then the results are much more statistically significant. Okay.
Can I ask you a quick question?
Of course, yeah.
Do you know the average number of the transactions when they got the treatment, like at this wrong feedback? Yeah, because this 4% looks like a really big number.
I think it's about 30 to 40.
30 to 40. Oh, okay, kind of makes sense because at the 40, if you get one negative feedback, actually
it actually hurts you quite a bit. Yeah.
Okay.
Yeah. Right. So what I wanted to say was that, we're like, when we see this result, we were actually quite happy because, if you think about our model, it was really like parsimonious, right? It wasn't really like a real full-fledged model. It's like everything is basic that generates a few predictions, which are exactly sort of seen, in the data. Even the intricate ones, like that after a decrease in prior, the probability that a given rating is negative increases, right? So even these sort of more intricate predictions are sort of seen in the data. So, and that's something that we're quite happy about. Okay, so now we have a second challenge, which is that, even though, under our argument, or if our argument was correct, wrong negative feedback is not related to underlying quality, but still sellers might change their behavior after observing this wrong negative feedback, right? Perhaps they feel discouraged and therefore they shirk and so forth. And that changes in seller behavior can still affect subsequent rating behavior. Okay? And the way that we deal with this is to essentially use the following research design. Okay? So we denote the time of first wrong negative feedback, right? So this should be all mistaken negative feedbacks by T naught. And then we're going to bucket transactions of the seller into 3 buckets around this T naught. So transactions in class 1, they took place before T naught, and they are also rated before T naught. And transactions in class 2, they happened before T naught, but they were rated afterwards. Okay. And lastly, for transactions in class 3, both the transaction date and the rating date are after T naught. Okay. So in a nutshell, the idea is that if we compare rating outcomes for those in transaction, for transactions like transaction 2 versus transaction 1, then because both transactions took place before the arrival of first negative feedback, and therefore sellers cannot endogenously change their behavior yet because they cannot condition their effort on something that hasn't happened yet. And therefore, we kind of control for seller behavior. But if we compare rating outcomes before for transaction 1 and transaction 2, the difference is that when I rate, or when a buyer rates, one buyer observes, say, 100% feedback score, whereas the second buyer observes 95% positive scores. And we're going to essentially quantify what's the effect of that on my rating behavior. Okay, and that's essentially what I'm showing you in this table. So the outcome variable in this table is whether a given feedback is negative, and we're regressing that on a class 2 dummy and a class 3 dummy. Okay, so the omitted group is class 1. So what this regression shows is that for transactions in class 1, which is after the arrival of a negative feedback, people are much more likely to leave a negative feedback relative to a positive feedback. And note that implicit in this design, we're only looking at transactions in which a feedback is left, right? Because we have to use the rating date to bucket the transactions. So here we're only looking at those transactions with ratings, and therefore this 1.05 percentage positive change should be interpreted as an increase in probability of leaving a negative feedback relative to the probability of leaving a positive feedback, right? So this is, to some extent, is a direct test of our second part of prediction 2, which says that which speaks to the probability that any rating is negative, right? And that should increase, which is directly shown in this regression. And then in the second column, we essentially want to understand what's the effect, or what's the heterogeneous effect by buyer experience, product characteristics, and seller characteristics. In particular, whether a seller had more than 73 positive feedback before receiving this negative feedback. So this sort of relates to what Jin was asking about essentially, what my prior is about the seller and how that mediates the effects. So the results here, we argue, is actually consistent with the Bayesian model in the sense that, if a seller has a very high prior belief, or if my prior belief towards the seller is high because he has had a lot of positive transaction or positive feedback before, then this imitation effect is kind of smaller, right? So it's saying that despite the fact that I'm having a negative news, I'm attaching relatively less weight to my negative signal compared to another seller that doesn't have that many positive feedback, in the past, and therefore this so-called imitation effect is actually not as big as compared to that seller without a strong prior. Okay, so this is sort of consistent with the Bayesian framework.
Sorry, can I ask a clarification question?
Sure.
So for class 2, the negative feedback happened after the purchase, right? So how?
No, sorry, the negative feedback happened after the purchase, before the rating.
So, okay, so it's not going to affect class 2's prior belief.
Sorry, by prior belief, I mean prior belief when he rates.
Okay, sorry. Yeah, I've been thinking about prior belief like at the time of purchase. Okay.
Right. So, so that's sort of the, in this current paper, we do not model this essentially selection at the purchase stage. So that's actually something that we're working on currently using some search data. But here we are focusing on, our point is that, assuming that a transaction happened exogenously, then we're going to see how belief updating affects my rating behavior.
Okay.
Right?
Yeah.
So,
otherwise, I can imagine like very dynamic like interactions, the prior belief with the previous ratings. Okay.
Yeah, I agree.
Gotcha.
Yeah.
Thank you.
Yeah, no problem. So I think I have a question. Oh, okay. Never mind. All right. Then we also did a few additional tests to make sure that our results is indeed driven by belief updating, but not something else. So first, in column 1, we, in addition, instead of just controlling for seller fixed effects, we control for seller by transaction date fixed effects. And the concern that we're trying to kind of alleviate is essentially seller learning over time, right? And the reason that we like these positive results alleviate that concern is because we're looking at transactions from the same seller on the same date, and under the assumption that a seller doesn't change his or her quality dramatically within the same date, then we're essentially controlling for these learning effects by looking at the same date. So that's sort of the argument in column 1. And in column 2 and column 3, we run a couple of placebo tests where instead of using a wrong negative feedback, we are using other wrong consumer reports that are either not as observable as classical feedback like DSR, or not observable at all, such as wrong claims. Okay, and we're defining class based on these wrong consumer reports. And essentially, the results shows that we can essentially nullify or make these effects disappear. And the fact that they disappear suggests that the imitation effect that we identified in the previous slides is really driven by the fact that buyers observe these public ratings and hence they update their prior belief, which leads them to rate more and more negatively, as opposed to something about the underlying quality of the seller. Because if that were the case, then that we would essentially observe similar results when we use classes that are defined by some other negative consumer reports. Okay, so that's sort of the idea. So essentially, the results here are consistent with the belief updating story. Okay, so in the last 10 minutes or so, I will talk about the simulation exercise and that we did. So far, we had a very simple reduced form model with some testable predictions. And essentially, our data from eBay are consistent with this empirical evidence. And now the reason for this simulation exercise is that, so suppose that, buyers know that this simple framework, right? Because, they use it, a typical buyer use this simple framework to rate themselves. And suppose that they also expect that other people also sort of having this thought process when they rate. Then under this assumption, we want to use the simple framework to answer a couple of questions, which is how fast can a buyer learn about seller quality when ratings are left selectively? And the related question is, how does online reputation, namely percentage positive in this case, and the prior belief for an average seller evolve over time? And the approach that we take in this exercise is to simulate ratings for the first 200 transactions of a given seller. And a couple of key assumptions that we are making is that buyers have full information on the entire history of transactions and ratings that a seller had. And we are also assuming rational expectations. Okay? So I know that these are not innocuous assumptions, but assumptions like full information is going to essentially dramatically reduce our exercises, right? Because otherwise you would have to integrate over all of the paths that have led to the same percentage positive score, okay, which is going to be much more costly to do. So the approach that we take in this exercise is, this calibration procedure that's typically used in macroeconomics, which is to fix some parameters and calibrate the others to feed key moments in the data. So essentially, these are the moments that we use to calibrate our model, such as the probability that a rating is left when t equals to 1, the probability that rating is left when t is 86, probability that a given rating is negative, and so forth. Okay? The parameters that we fixed are these rows, and lambda is the initial belief that any seller on the platform is of high quality, right? So essentially we fix this in our simulation exercises, and then we also vary these values to see whether the results are robust. And the parameters that we're going to calibrate using moments in the data are these utility parameters. Okay. So let me show you some basically key insights of the exercise. Okay. So first of all, in this graph we plot the probability of rating as a function of a seller's transaction index. Okay, so this is the average across 10,000 simulated paths. Okay. So a nice thing from this figure is that we did fit the probability of rating when t equals to 1, and we also sort of try to fit the probability of rating when t equals to 86, but we didn't target the shape of this curve, which actually comes out nicely and have this convex shape, which is very similar to the data that we observe on eBay. So that's sort of reassuring and suggesting that we're not doing something super crazy with this calibration. And here's the results I want to show you. Okay, so here we can simulate a seller's rating over time, right? And this is for a good seller and for a bad seller. And the dotted lines are essentially the two rows, right? So this is the share of transactions that are good, 95% for a good seller, and the share of transactions that are good for a bad seller. Okay? So we see that percentage positive ratings lie consistently above the true share of good experience, right? So in this sense, ratings are biased. However, despite that, when we sort of simulate the prior belief for good and bad sellers, we see that buyers actually learn about their type relatively fast, right? In particular, in about 100 transactions, they are like 90% sure that a good seller is of high type, right? So this is kind of saying that, despite that, ratings are biased, as shown in the previous graph, to the extent that buyers understand this, simple Bayesian model that I sort of just showed you, they do not interpret this percentage positive literally, and therefore they can, essentially learn about a seller's type still relatively fast, despite the fact that these ratings are biased, right? So when they see 100% positive feedback, they do not interpret it literally that 100% of the transactions have been good. Okay, so that's sort of the point. All right, so let me sort of conclude by sort of pointing out that there's a very vast literature on rating, and the central theme there is to understand how the distribution of rating relates to the distribution of experience. Okay? So the contribution of our work is that we argue that the informativeness of online reputation score is going to depend on the process through which the ratings are given. Okay? And to make this point, we essentially did three things in the paper. So first, we provide a reduced form Bayesian model that explains some key aspects of rating behavior. And secondly, we take these predictions to the data on eBay and find some supporting evidence. And lastly, we assume that the model is true and calibrate the model to key moments in the data. And the exercise shows that buyers may learn relatively fast whether a seller is of high quality, even if aggregate ratings are biased. Okay. So that's all I have for my presentations. And if you have questions, I'm happy to answer them.
Hi, Xiang, I have a question.
Yep.
I think a very good paper, very solid research designs. And
Thank you.
If we think about the platform's incentive to not necessarily manipulate it, but at least somehow maybe they can choose to show more positive or negative. So I mean, what your results can tell for like what's the optimal way of designing this rating mechanism for platform if
Right.
they have some or even if their goal is to provide correct information or more informative signal for buyers. So can platform learn something from here?
Right. So that's a very good question. So that's also something that we are thinking about, right? Because that's sort of gives policy implications for platform. So one thing that we have been thinking is to essentially so first of all, based on our model, we show that as a seller becomes more established, the likelihood of a buyer sharing her negative experience becomes smaller, right? So essentially, one thing the platform can do is to essentially weigh this less likely negative feedbacks that happens when the seller is old or established on the platform by the inverse probability of that happening, right? Because according to the model, we know that they are less likely to happen because buyers are less likely to have a deviating posterior when the seller's prior is high. So that means that when they happen, we should kind of give them more weight in the aggregation of reputation score, and that more weights should be the inverse of the probability of that occurring, right? Of essentially the probability of sharing a negative experience, conditional on you have a negative experience for different transaction index, right? For sellers with different seniority. So that seems like a direct implication of our results. Yeah, and of course, there has been some similar arguments in the previous literature, which is to kind of look at a shorter window, right? A shorter look back window to sort of reduce the effect of seniority or having a lot of past transactions on outcome. although a lot of the arguments there focuses on this moral hazard story, right? So essentially, in sellers' late career, they were going to have moral hazard because, if we are just taking a simple average over their entire career, then what they do today is not going to affect their reputation score that much. Therefore, they shirk, and that's why, we should have a tight window. Whereas, in our paper, we also argue that, we should kind of have a tight window, but our argument is sort of different. It's coming not from the fact that sellers will shirk in their late career, but coming from the fact that, essentially a buyer will be more likely to give up her own transaction signal as the prior increases, right? Which is a function of the window length that we look back to. And that's going to essentially at some point decrease the informativeness of the rating, because buyers will not share their negative experience because they're not sure, whether it's their thoughts or and so forth. So I guess that's another implication, which is to shorten the look back window when constructing these reputation scores.
Yeah, actually, I have some question. So I think one of the concerns from this rating system in online platform is it can create some kind of the herding behavior. So if you have a lot of the review, and that's gonna collect more consumer, and they're gonna leave more reviews on there. So just maybe few sellers gonna collect all the consumers and the reviews. But in your kind of world, by your model, this Bayesian model, it's less likely to happen, because once certain amount of the reviews are accumulated, consumers not gonna leave the review up there.
Mm-hmm.
Yeah, is it?
Right. So that would be the prediction of our model. So I'm not sure. So the herding story that you're telling, was it sort of driven by the search ranking algorithm that, if, let's say, listings with more reviews would be more likely to shown on top of the search result page, and that's going to attract more buyers and hence more ratings?
Yeah. Actually, that's a different story, because if you have some more review, that's going to collect more consumer. It's not the part of your model, right?
Right. It's sort of a halo effect where, momentum attracts more future sales. So I think that's interesting, but it's sort of not the focus of this model. Yeah.
But what your paper says that even after they come to the seller who has some certain amount of review, let's say 100, they are very less likely to leave additional review because they already know their prior, maybe.
Right. They're less likely to leave review, right? Because if you think about the figure 1 that I showed you, if we move from first transaction to the 86 transaction, the drop is about from 70 percentage points to like 65 percentage points, right? So still people are going to leave review 2/3 of the time. It's just that compared to the first transaction, there's a 5 percentage drop over 70 percentage baseline. Right?
Okay.
And so essentially that's, we think of that as some sort of fixed effects, right? That, essentially some people just leave feedback. So that's something that our model does not explain. But what our model explains is that, as your prior changes, what is sort of the directional effect of your rating behavior.
By the way,
Oh
no, yeah, just go ahead. Yeah.
Oh, sorry. Yeah, I have a follow-up question related to that. The herding behavior from the sequential observational learning, and I was wondering, what's the case here? Does you assume all buyers observe all the previous review, or they just have they can look at the average the average rating and with the number of reviewers?
So in the simulation exercises, we made that assumption to make the exercise easier to do. But in our main analysis, which is the identification of the effect of belief updating on outcome, there we don't assume that people have to observe the entire rating history, right? So we actually also in our model, we only need buyers to receive some sort of public rating scores that satisfy a few general assumptions. It does not have to be the full history of feedback.
Is there any other questions out there? Yeah, seems like yeah, we are done. And thank you very much, yeah, Professor Hui. That was excellent. Yeah, presentation and also paper looks really interesting. Yeah, thank you very much.
Thank you very much, Xiang Hui, and thank you all for and Xijie, especially Yingju and Jin for all the questions, and also Xuan for all the lively discussions. I appreciate that.
Okay. Okay. Yeah. Thank you.
Thank you.
Yeah,
Thank you very much.
Thank you. Bye.
Bye-bye.